Welcome to Standardized Scores. In this video, we're going to explore what's known as z-scores. They're very important statistics. They're actually one of the most valuable statistics in all of statistics, so you should probably talk about it. All right, so what is your position? Knowing a particular value's position and the data set it came from is extremely valuable information to have. Now, we've already learned that a percentile can help us with this. For example, you take a test and you score at the 88th percentile. That 88th percentile tells you your position in the data, because we know that 88% of all test takers fell at my particular score or lower. 12% were higher. So that instantly tells me I'm towards the top. I'm not at the tippity top, but I'm definitely at the top where there's only 12% above me, 88% below me. So this gives us a better understanding of where your score fits amongst others. Great information to have. But we have a second way we could do this, a second way we could determine where you fit in the data. What's your position? And that is known as a z-score. Now, the official name of a z-score is a standardized score, but we call it a z-score. Now, why didn't we call it an s-score is what a lot of kids ask me. Well, we were already using s for standard deviation, and t and a and nd just seemed too boring, so we went with the z, a standardized score. So that's where we get the name z-score from. So a z-score is a measurement of how many standard deviations a data value is from the mean. I repeat that 20 times to yourself right now. What is a z-score? It's a measurement of how many standard deviations a value is from the mean. You could be above the mean, you could be below the mean. A z-score is simply measuring how many standard deviations you are from the mean. So how do you get a z-score? Well, it's really easy. To get a z-score, we simply take our value. So x is just, your particular score, your particular height, your particular weight, whatever it is. It's the value that you're interested in, and you subtract the mean. So the numerator is how far you are from the mean. Positive, you're above the mean. Negative, you're below the mean. Divide it by the standard deviation, and it will tell you how many standard deviations you are from the mean. Pretty simple formula, really easy formula. Again, take your value, subtract the mean. That'll tell you how far from the mean you are. Divided by the standard deviation, now you have an idea of how many standard deviations you are from the mean. Let's talk about a couple facts about z-scores. First off, they have no units, because in the numerator, you are in the same unit as your problem. So maybe I'm 150 pounds, I subtract the mean of 120 pounds, I got 30 pounds, okay? Standard deviation, that's also measured in pounds, so when you divide, that unit is going to reduce or cancel away. So there's no units on z-scores. It can be positive if your data value is above the mean. If you're above the mean, you're going to have a positive z-score. If you're below the mean, you're going to have a negative z-score. Now, we talked a lot when we first learned about standard deviation, that standard deviation is how far typical data is from the mean. And we said 1. Typical, most data is within 1 standard deviation of the mean. Well, now we could say that that's 1 z-score. That's a z-score of what? How many standard deviations are you from the mean? Oh, I'm 1 above. Well, that's your z-score. I'm 1 below. That's your z-score. And we know that it's very common, very normal, very typical, very usual to be within 1. So if you have a z-score of -1 to 1, that means you are within 1 standard deviation of the mean, and that's where a lot of data is. Now, if we expand that to -2 and +2, so if we are within 2 standard deviations of the mean, that's a z-score of -2 to a z-score of +2, that is also very typical. That's not unusual. It's not strange. A lot of data is within 1. If we advance that out, we do get more data, but it's not unusual to be in that range. If you're within 2, you're pretty standard, pretty normal, pretty typical. Now, it's when we are outside of 2, -2 or +2, that you become strange. We actually said that's one of the ways that you could quantify something as an outlier, is if we have a z-score, because now we can actually name that, the number of standard deviations a value is from the mean. If it's more than +2 or less than -2, that's where we say, whoa, that's a strange value. That would be considered an outlier. And then if we expand that to 3, so if you're outside of 3 standard deviations from the mean, above or below, that would be very, very, very unusual. Extremely unusual. All right, now a couple more facts. So we've already mentioned this again. I just want to keep reiterating it, is that a good chunks, I want to define it right now, but over 50% of data is within 1 standard deviation of the mean. Again, a pretty big chunk of data. So that's a z-score of -1 to 1. If we expand that to 2 standard deviations from the mean, that's a lot of data. I mean, a ton of data. I don't want to give an exact percentage because it all depends, but there's a big chunk of data. And then if we expand that to 3, be honest, in most data sets, that's pretty much going to be all of your data. All of your data should be within -3 to +3 standard deviations from the mean. That is why we say if you're outside of 3, we're like, whoa, what's going on? That's pretty strange. So another really important fact about z-scores is if you change the data, you could change the data all you want. The z-score, which measures your position in the data, will not change. So imagine that we take all of our values and we multiply them by 6, subtract 3, add 15, right? We change our data. But if all the data is being changed, then wherever I fit into that data is not going to change because I'm going to move with all the other data. If I go up, I go up. If I go down, we go down. If we multiply, we divide. It doesn't matter, right? Because a z-score is a measurement of your position. And as long as all of your data is changing the same way, your position in the data won't change. So if I have a z-score of, let's say -2, that means I'm 2 standard deviations below the mean. If all of my data collectively goes up, down, left, right, wherever, then my position is still 2 standard deviations below the mean. Now, if you move your data, your mean can change, your median can change, your standard deviation can change, your IQR can change, your range can change, all that can change. We've talked about that in the past, but the one thing that will never change is your z-score. All right, let's dive into this a little bit deeper. So why are z-scores so important? Imagine you take a test in a college class with over 100 students and you get a 78. That information alone doesn't really tell you a whole lot. Like, okay, I got a 78. Is that good? Is that bad? Where do I fit in amongst all the scores? Because that's what's really important is not just what you got, but what's your position. So is 78 a high score, low score? Is it a typical score? I really don't know. And that's where the z-score could give you so much more detail. So let's look at 4 different situations here, 4 different scenarios. So in all the scenarios, you got a 78. But let's see how your position changes based on the mean and the standard deviation. So in red here, we have a mean of 80, standard deviation of 5. So my z-score is going to be taking 78 minus 80 divided by 5. Now, if you are going to use a calculator for this, I highly encourage you to do the numerator first, right? So 78 minus 80, hit enter, or just know, hey, that's -2, and then divide by 5. So that's a z-score of -0.4. So obviously I did a little bit below the mean, but it's not that far below the mean. Like -0.4, that means I'm pretty close to the mean. I'm less than 1 standard deviation from the mean. And again, remember, we mentioned that most data is within 1, -1 to +1. So I'm well within that. I'm only 0.4 standard deviations below the mean. I scored a little bit below average, but it's not like I'm way at the bottom. Now, what if I had a mean of 80, standard deviation of 0.5? So that's a z-score of, let's see, I'm going to take my 78, subtract the 80, divide by 0.5. Again, grab your calculator, do the 78 minus 80 first, -2, divide by 0.5. And this time I get a z-score of -4. Holy crap, that is extremely unusual. That should never happen. That's unbelievably low. So I mean, I should kind of be embarrassed. Maybe I should drop the class because I bombed the test. I mean, that is unbelievably terrible. I talked about it's very strange to be 3 standard deviations below. -4 would be like the teacher should be hopefully talking to me about what I could do because I bombed the test. So in both situations, I scored below the mean by 2 points. But it's really about the spread. When the standard deviation was 5, remember that means we could take 80, go down 1. Standard deviation, that takes me to 75, go down 2, that takes me to 70, and again, that's all pretty typical. But if my mean is 80, my standard deviation is 0.5, when I go down 1 standard deviation, that's only 79.5. If I go down 2 standard deviations, that's only 79. So in that situation, no wonder a score of 78 is really, 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 really low. Again, this shows the value of what z-scores do for us. All right, here's another example where the mean was 95. So once again, what's my z-score? I'm going to take 78 minus 995, divide by 12. 78 minus 95. Do that first, either in your head or on your calculator, then divide by 12. That is -1.417. So I did bad. I did below the mean, but it's inside of what's typical. Remember, anything from -2 to +2 is pretty normal, not that weird. But again, at the end of the day, I still scored towards the bottom. All right, here's another one. This time the mean is 70. Standard deviation stayed the same. So I got a 78. So right away, I know that I did better than the mean. Divide by 12. 78 minus 70. Do it in your head. Do it on your calculator. Get 8. Then divide by 12. That is 0.667. And just for future reference, I like to round my z-scores to 3 decimals. But again, now we see I did better. I did positive, right? So this was actually above the mean. And just a little bit though, right? I wasn't like way above, but I was a little bit above. So this is where z-scores really kind of tell us a better idea of where we fit in the data. Notice there's no units on any of these z-scores. It's really about how many standard deviations you are from the mean. Here, I was way below the mean. Here, I was just a smidgen below the mean. This is, again, below the mean, but, you know, so it's like a scale. Think of a scale, right? And in fact, it's a universal measuring stick. Z-scores really are this universal measuring stick. It's this scale with 0 in the middle because think about this for a second. If you actually score at the mean, then you are 0 standard deviations from the mean. So a z-score of 0 means that you fell at the mean. So that would be the mean right in the middle. And then we go up 1, we go up 2, we go up 3. I mean, I could put a 4 on here, but again, I already talked about the fact that's very, very unusual. Down 1, down 2, down 3, down 4. Again, no point really putting that 4 there, but you get the idea. And now that we have this universal measuring stick, there's no units here. It doesn't matter if you're pounds or ounces or feet or miles. It's one measuring stick that can be used to compare anything. And the further you are to the right, the higher above the mean you are. The further you are to the left, the lower you are. And again, we know that a big chunk of data is within 1. A really good chunk of data is within 2. And, you know, out here, it's just very, very little data. Very, very little data. Very, very, very little. There might be some data above positive 2, but again, not a whole lot. The majority of data is within 2. So that's why when you have that z-score of -4 or +4, you're like, what the heck's going on here? Now let's do an example. We can actually see how it really is this universal measuring tool. So what's bigger, cat or dog? Well, it's that's not a fair comparison. Can't compare a cat and a dog. Cat's a cat, dog's a dog. You're right. But if I use z-scores, I can compare them. So a dog weighs 54 pounds, and the mean weight of all dogs of this type is 45 pounds, with a standard deviation of 5.4 pounds. So what's this dog's z-score? Take the weight of the dog minus the mean of the dog, divided by 5.4. Grab your calculator. 54 minus 45 is 9. Then divide that by 5.4. We get a z-score of 1.667. So this is a dog that's on the higher side. It's not quite to that 2 where it's like, oh, that's pretty high. But it's close to 2. 1.667 is pretty close to 2. So this is a bigger dog. But let's take a look at this cat now. This cat weighs 22 pounds. The mean weight of all cats of this type is 16. So I'm going to subtract the 16. Divide by the standard deviation of 2.4. 22 minus 16 is 6. Divided by 2.4 is 2.5. That is an enormous cat. That's a really, really, really big cat. That's outside of 2 standard deviations. It's 2.5. So now, you know, when you would think, oh, I can't compare a cat and dog, they're different. You actually can with z-scores. So if I'm comparing this cat and this dog, that cat is a really big cat. Now, even though the cat doesn't nearly weigh as much as the dog, duh, but that's not fair. It's not fair just to compare 54 and 22 because one's a cat, one's a dog. I know it's both pounds, but they're different animals. Where if we put them on this universal measuring tool called a z-score, now it's really fair to compare them and say that cat is way bigger than that dog. So z-scores really do allow for this fair comparison, right? A really true fair comparison in our data. A lot of scoring systems are going to z-scores. You know, for example, in the Olympics, when they do the triathlon or the decathlon, when there's multiple events and you're trying to, how do I compare people's scores across multiple events? Use z-scores. It's a fair comparison, whether you're dealing with the time it takes to run a race or how far you could throw a shot put. In other competitions, if you think about it, sometimes you just want to beat the person behind you. But if you're using a z-score, you actually want to really push to the end and not just beat the person behind you. You want to beat the person behind you by a lot, because if the winning score is not just, hey, I finished first place, if the winning score is my Z-score, well, then I want to do better comparatively to everybody else, not just to the person behind me. The more I could do better than everybody behind me, the higher my Z-score is going to be and the better I'm going to do. So a lot of different things, organizations are going to Z-scores to compare data. Now, one final thing I want to comment on here is Z-scores can be used with any data. Like the shape doesn't matter, right? Doesn't matter. You use Z-scores. All you need is mean and standard deviation. You got Z-scores. But when you do have normal data, remember normal is symmetric and unimodal. So we see this is very symmetric and very unimodal. Giant hump in the middle. This is when the Z-scores are very nice, right? Because we see a 0 is smack dab in the middle. Like it couldn't be more in the middle. And we get this idea that if we go up 1 or we go down 1 standard deviation, we get a big chunk of data. We can actually see it. And that's what's nice about using the normal model in this situation, is we can actually see that big chunk of data that I'm talking about. And then if we go down 2 and up 2 standard deviations, we see that in between 2 and -2 is also a really big chunk of data, literally almost all data. And then finally, if we go down 3 and up 3 standard deviations, we see that at this point, we have captured literally almost all of our data. And that's why we say that almost all data is within 3 standard deviations. Now, if we fall over here or over here, that is where you're like, whoa, that's unusual. And we can actually see how unusual that is, because look, there's just very teeny bits of data over here. Extremely unlikely. But in a normal model, in a normal symmetric unimodal set of data, this is exactly what it's going to look like. So you're probably not going to see a -4 or a +4. Okay, I guess it's not impossible, but extremely unlikely. But when you do have normal data, there does need to be data that gets down here, and there does need to be data that gets up here, just not a whole lot of it. Most data is within -2 to +2. That's where most data is. So again, Z-scores can be used no matter the shape of the distribution, but when your shape is normal, it's just a little bit more specific and a little bit more balanced when we look at this, with that 0 being in the middle, down 1, up 1, down 2, up 2, down 3, up 3, where we actually see, based on the area, where the data is. We can actually see, like right here in this yellow region, we see that there's definitely data down here. There's data down here, but not nearly as much as up here. And that's kind of the cool thing about when your data is normal. All right, so more on that to come, obviously, but hopefully you understand what a Z-score is. Super easy formula to find one. I actually want to show it to you one more time here. Really easy formula, and make sure you know the definition. It's how many standard deviations from the mean your data is.